Today we are going to talk about the n-butyl stannous hydride. So this is one of the powerful free radical reducing agent. So how the reaction works. So now we'll see the mechanism. After that we'll see some of the examples where we use n-butyl stannous hydride for reducing the other functional groups. So in the mechanism, so this n-butyl stannous hydride requires initiator. So that initiator is AIBN. It means azo bis iso butyro nitrile. Okay, so the structure looks like this. There is a N double bond N, this is CN, and this is CN. This is the structure of azobis isobutyronitride. So this when we expose this one to a photochemical light or thermal condition, so it releases N2 and it forms 2 moles of this free radical. Okay, and this free radical reacts with the Bu3SnH, and this free radical abstract this proton. So now it becomes Cn, here hydrogen, plus Bu3SN radical. Okay, so now this Bu3SN radical reacts with alkyl halide. Here I am writing. So we have alkyl halide plus Bu3SN radical. So here this halogen will be abstracted by the this Bu3SnH, and it leads to form Bu3SnX plus alkyl radical, and this alkyl radical further reacts with the Bu3SnH, and it abstracts this hydrogen, and it leads to form a hydrocarbons. So this is the mechanism for n-butyl stannous hydride, how this is reacting. So initially we have a initiator, that is azobis isobutyronitride, and when we expose this one to the photochemical light, so we are getting a this free radical species by elimination of this N2, and further this reacts with Bu3SnH, this abstract this hydrogen, and we got this compound, this free radical, and this free radical abstract halide from alkyl halide, and it leads to form alkyl free radical. So this alkyl free radical reacts with again one more Bu3SnH, and it leads to form a alkyl halides. So this is the mechanism for n-butyl stannous hydride. So we'll see some examples now. So in the first, like how alkyl halides converts into hydrocarbons. hydrocarbons. So here we have one example, iodine plus so this in this reaction what could be the product. So here we can go through the mechanism. So initially n-butyl-stannous hydride that abstract this iodine. Okay, so we have here Bu3SnI after abstracting this iodine, and here we have cyclohexyl free radical. So in this next step we have alpha beta unsaturated carbonyl compound. So here if you do the homolytic cleavage of this bond, so we'll get this free radical. So now there are two possibilities where in the first case imagine that this form a bond with this free radical, and in the second case imagine that this free radical forms a bond with this free radical. Okay, so take it as this one is A, this one is B. So in this A path, so we'll get CH2 here radical COR. So in the B path we'll get this is forming a bond, that means here radical comes COR. So here which product is major, that we have to identify on the basis of free radical stability. So here this free radical is primary free radical, here it is a secondary free radical, and so we know the stability of free radical, tertiary is more stable than secondary than primary. So in this step we are generating the more stable free radical. So because of that reason this beta attack will takes place. Always remember when we have a alpha beta unsaturated carbonyl compounds in n-butyl-stannous hydride, so always beta attacks takes place. If beta attacks takes place, we are generating a more stable more stable free radical. And this now one more n-Bu3SnH comes, this hydrogen goes and attacks to this free radical, so that we'll get this product. And this is not stable, so we no need to discuss about this mechanism, nothing. Here also n-Bu3SnH comes, hydrogen goes here, so we'll get a methyl group there. So this is the one example. And then we have next example, OAC. So in this case the driving force is a ring strain, because cyclopropane ring is unstable. So because of that reason this ring get cleaves. So initially we have a free radical here after iodine abstract by the n-butyl-stannous hydride. So here pH, here OAC. So now there are two possibilities are there. This ring can break, this ring can get break like this, or this can also get break. Imagine this is A, this is B. So in the A path, A, B. In the A path, this bond is getting break. So this is pH, this is OAC, this is methyl group here, and here we are getting this kind of compound. And in the B path, this bond is getting break, OAC, here radical, pH, and then these two forms a bond and these two forms a bond, and here we'll get this product, and here this product. Now which is major? So here we tell the product is major or not based on the free radical stability, and here free radical is there and here also free radical is there. So which one is more stable among these two? So this is more stable. Because of that reason this forms, but this will not forms. It may forms but it's very less because it's unstable. And further another n-Bu3SnH gives hydrogen to this carbon, so we'll get a hydrocarbons. And now whatever example I am going to talk, it's very important in the examination point of view. This one, Bu3SN radical abstract this bromine. After that we have a radical here. So now this bond gets breaks. Now if there are two possibilities, these two can form a bond or these two can form a bond. Okay, if these two forms a bond you will get a 5-member ring, and if these two forms a bond you will get a 6-member ring. Okay, um, if it form 5-member ring, this is the product. If it is 6-member ring, then this is the product. And remember, this one forms at 81% and this one forms at 2%, because we know that cyclopentane is a angle strain free molecules. Okay, so because of that reason 5-member ring formation is favorable over the 6-member ring formation. Okay, this is important. And then we have two examples here, important examples. Here methyl group and here radical is there. And another example is here methyl group is there. So now similarly we will do the homolytic cleavage here, and here also homolytic cleavage. After homolytic cleavage we get the radicals. Now here also same 5-member ring forms in more amount compared to 6-member ring. 5-member ring means 1, just start numbering from here, 1 2 3 4 5, 1 2 3 4 5. So at the second position methyl group is there, and at 5th position another radical is there. Further it gets converted into methyl group after giving a hydrogen, after taking one hydrogen from this. Okay, and here also same, here also same, we'll get 5-member ring, 1 2 3 4 5. So 1 2 3 4 5, methyl group is there at 3rd position and 5th position. Now stereochemistry is very important here, whether it is a cis or means whether both are cis or both are trans. So in order to identify the stereochemistry, we just draw them in a cyclohexane form, like chair form, open chair like this. Okay, this we can write like this, and here methyl group is down the plane. And now after homolytic cleavage it becomes like this. So these two are forming a bond, right? And here we can see a methyl group at fifth carbon. This is fifth carbon. This is first, second, third, fourth. A methyl group at a fifth carbon is above the plane, and a methyl group at second carbon it's below the plane. So these two comes in the transfusion, and fifth carbon will be above the plane. And similarly, here also, like this, 1 2 3 4 5. So at fourth carbon, at 1 2 3, at third carbon, methyl group is above the plane, and now these two are forming a bond, right? And we can see methyl group at fifth position as well as third position, they both are in above the plane. So this here will get cis product, and here we'll get trans product. So these are the two important examples for n-butyl-stannous hydride. These questions asked, I think, in a previous exam. And next example, here we have iodine plus pH and pH. So here we are treating with the n-butyl-stannous hydride. So we know that here we will get a this radical, and this gets a homolytic cleavage. Okay, so now here two like this radical is there. So here two possibilities are there for this. It can forms a bond with this free radical, or it can form a bond with this free radical. But the one point you just remember that after like here we have to generate the stable free radical. So this is the stable free radical. So in order to generate the stable free radical, this has to form a bond with this free radical. So now we get this compound, double bond O, double bond O, pH and pH. So here we will get a this compound. So here free radical comes, and this free radical further takes one hydrogen radical from n-butyl-stannous hydride, then it gets converted into hydrocarbon. And what about the stereochemistry for this? So here we'll get see here already this group is present above the plane, and this should come below the plane. So this is the stereochemistry in this case. And then next we have this, also important, Br methyl OH, and here we have cyanide. So now Bu3SN radical comes, that takes this bromine, methyl group here, this cyanide OH, and here we have this radical. So now this homolytic cleavage takes place. So here also we'll get a 5-member ring, and these two forms a bond. We'll get a 5-member ring. So here cis geometry is a major. So when we have a two 6-member rings like this system, here trans is more stable. We can see hydrogen is here, hydrogen is here, and this is equatorial and this is equatorial, so they both are in the trans position. So when two 6-member rings are fused, in that case we have a trans stereochemistry that is the more stable, whereas for one 5-member rings, one 6-member ring forms, that time it forms like this. Okay, and see here in this case this is below the plane and this is the above the plane. In this case this is below the plane and this is also below the plane. So because of that reason, when one 6-member ring, one 5-member ring is fused, that time we will get cis stereochemistry compared unlike two 6-member rings. So here two 6-member rings we will get a trans stereochemistry. And then we see some intramolecular reactions. One, two, alkyne is here, then iodine. So in the first step we have Bu3SN radical. This will take this hydrogen, nitrogen. So now this bond goes for homolytic cleavage. And then here radical, here also radical comes, methyl, and these two fuse together, we have a one 5-member ring here. And further we have another reaction here. This also we do the homolytic cleavage like this. Okay, so now just count it. Here also 1 2 3 4 5 6. If these two forms a bond, we'll get a 5-member ring. If these two forms a bond, we'll get a 6-member ring. So just remember, 5-member ring is more stable compared to 6-member ring. So that's why here also we'll get a this will be major here. So this is the final product, and here we have to see this stereochemistry. Just remember, when we have a two 6-member ring, in that case trans stereochemistry is major. When we have a 6 and 5-member, cis is major, because I have explained here. And when we have two 5-member rings, then also cis is major. Okay, so here we have cis and cis, and when we have a when we have a three 5-member rings are fused together, so now the stereochemistry will be here cis trans cis. How cis trans cis? So this is 1 2 3. So one position this is cis, third position also this is cis, and second is trans. That means this hydrogen is trans to this hydrogen is trans to this. That's why cis trans cis. So when we have a three 5-member rings are fused together, in that case we will get a cis trans cis stereochemistry. Then CO2 ET Br, this is OCOPH, like this is there. So here radical will comes here, and this bond gets break, homolytic cleavage. Just give numbering like 1 2 3 4 5 6. If these two forms a bond, we'll get 5-member ring. If these two form a bond, we'll get a 6-member ring. And the final product what we will get here is CO2ET, COPH. This is one product, and another product will be OCOPH. Just remember here, it's already in the starting product. We are have already above the plane bulky groups we have. So here this CO2ET is here above the plane, and here it's a below the plane. So in case of n-butyl stereochemistry is very important. So here, since this is already bulkiness is there above the plane, this will be minor. Here no steric crowding, means like this is below the plane, that's why this is the major product. And we have another example for intramolecular addition reactions. Intramolecular reaction followed by beta elimination. Intramolecular followed by beta elimination. Okay. Br or Bn so we have this compound. In the first step, this radical abstract this bromine. Now we have radical here. One, two, three, four, five. 1 2 3 4 5. So now this bond we do the homolytic cleavage, so we'll get like this. Now just give the numbering 1 2 3 4 5 6. If these two form a bond, we will get a 5-member ring. Always remember 5-member ring formation is major. COPH. And after that we have SPH. Sorry, SPH. Okay, now this is alpha beta. So intermolecular reaction is done. Now beta elimination. So after this beta elimination, here also we'll get a radical, and it leads to the final product like this. It's the final product. So likewise here also we have one more example. So here we have these two radicals, this radical, and now this forms a bond like this. These two forms a bond, and this will be taking a hydrogen from n-beta stannous hydride, so that we will get a hydrocarbons. And one important reaction after this I am going to talk. There is chance that you make a mistake here. So this is same, but here we have a phenyl group in the second example. Now, so here two possibilities are there, like if these two form a bond, we will get a 5-member ring. If these two form a bond, we will get a 6-member ring. So here we get a 5-member ring, okay, not a 4-member, sorry, this 4-member ring. So here we get a 5-member ring. If these two form a bond, we will get a 4-member ring, but that is not possible here. But here what happens, this free radical is more stable because this is adjacent to the phenyl ring, so this will not involve in the reaction. So here formation of 4-member ring is more favorable over the 5-member ring, because the free radical which is very close to benzene, that will not involve in the reaction. So that's why here we'll get a 4-member ring. So this is the product here. And then there are some other examples. So I am not going to draw the mechanism for them. I am just writing direct product. So here you will get this product. And then SO2AR BR, here you will get CH3. Initially you will get radical here. Now 1 2 3 4 5. So this 6 carbon is this one. And then so here initially you get a radical, and 1 2 3 4 5, these two form a bond, and finally we have this product. And you can practice these examples. NHOB, and this is this example. You can practice it and write the product for this. And also one more H. So here in this example what will happen, this gets break, here free radical forms, here also radical comes, here radicals. So just make sure that you should get a 5-member ring. If you connect these two, you will get a 5-member ring. Okay. And one last example, here we have, here also same, we have SPH here, N, So here we'll get a, this carbon will get free radical, and this also, and these two combines together, so that we'll get a 5-member ring, and here methyl group. So this is about the n-butyl stannous hydride. I hope it's clear. If you have any doubts, you can give in